one of our planet's most pressing concerns is climate change. We need to foster an energy transition from fossil fuels, such as coal, petrol, or gas, into renewable energy sources. If we look at the energy our world obtains today and consumes, we can see that it has been skyrocketing since the last century. We burn a lot of fuels, and that generates great amounts of CO2 that we release into our atmosphere, warming our planet and endangering our ecosystems. What if I tell you that we could make use of all the CO2 that we release, and by combining it with hydrogen coming from renewable energy sources, turn it into fuels? My team, collaborators, and also many scientists worldwide are trying to tackle this challenge. But in our case, we take quite of a particular approach. And I would like to dive you into it by using a futuristic vision. Imagine we can actually engineer materials with an atomic precision, and actually have a playground where scientists can virtually manipulate atoms as desired. A revolution, having a digital laboratory at our fingertips. The techniques we use drive us or lead us into the world where computers and algorithms meet the wonders of chemistry. That is the realm of computational chemistry. While I was starting with some futuristic vision, let me give you an example of how actually computational chemistry already has an impact in our society. For instance, developing a new drug takes several years of trial and error in the lab. And by screening virtually thousands of molecular compounds using computers, we can greatly save time and a lot of resources. But in order to actually understand the story and where we are today, I would like to rewind a bit and start with chemistry. Chemistry is everything, all the matter there is. And it began in the era of alchemy, where we were actually trying to turn metals into gold. Well, unless you correct me, nobody could actually achieve that. And if you know, please let me know privately by the end of my talk. Nevertheless, modern chemistry has advanced much more, being a driving force of food production in pharmacy, science, material development. Thanks to Mendelev's work, we organize the elements in the periodic table, combine them, synthesize new exciting compounds for the benefit of the humanity. But most of this progress came actually from without actually understanding how an atom it is in detail. Let's take the simplest chemical element, that is the hydrogen atom. It has a nucleus in the center and an electron around it. Back in the last century, the physics of the atom was actually unknown. And the breakthrough came with the development of quantum mechanics that showed that a completely new physics, and somewhat a funny one, was actually needed to understand how the atom behaves in detail. The breakthrough came actually by considering that an electron is not only a particle, like the one you see here in the box, but that electron around our nucleus also behaves as a wave, like the one you have if you pull the two ends of a string up and down, or the one you get if you throw a stone into a pond. Here in Vienna, it is actually the perfect place to tell you that an Austrian physicist named Erwin Schrödinger provided actually an equation to describe that. I will not go into the math, don't worry about that. The key idea is that there is actually an equation, which on one side, it tells us the energy of our electron wandering around, while on the other side, it tells us how this energy changes with time. With that, what we can get are kind of the probability of finding our electron around our nucleus, and also the energy it has when it occupies such a level. This development led to Paul Dirac, one of the founders of quantum mechanics, to actually state in 1929, the fundamental laws necessary for the full understanding of chemistry are thus completely known. But why would you ever need a supercomputer to get an answer for that? Well, the sentence of Dirac had a follow-up, and that is, the difficulty lies only, quotation marks, that the application of these laws lead to equations that are actually too complex to be solved. That means that, for instance, we can only get an exact answer for the equation for the hydrogen atom, where there is only one single electron. So all the rest of chemistry, where there are much more elements around them, it's not actually possible to be described. Then what scientists did was to actually approximate the equation. That is, finding a solution that is close enough to describe reality. If we take the next example, a hydrogen molecule, which has two hydrogen atoms side by side, two former students of Erwin S. Röntgen could actually show that you could actually get an approximated solution to the equation, and the energy these atoms have as a function of the distance. So we can keep track of the energy of the electrons. Since then, and to cut a very long story short, science kept evolving, and that led to the Nobel Prize in Chemistry in 1998. Walter Kohn, born in Vienna, and John Pople, from England, received the Nobel Prize in Chemistry for their contributions into computational chemistry. Kohn provided a way to approximate the equation even better and to be able to describe materials which contain more and more atoms, while John Pople was able to develop the first algorithms and the first computational code to run this in a computer. So let's look at chemistry and what all these developments lead us to. A reaction, if you simplify a lot, is nothing else than two species that we can call A and B joining together. And what they do is just follow somewhat of a hill, and that gives us to the products. The two atoms have joined together. So by using all this approximation, we could actually keep track of the energy of the electrons along the way. That is nice, but actually, there was actually also an ongoing technological development, and that is the increase in computational power, which has been dramatically increasing since the 90s, as you can see here in the graph. We are now able to treat more and more complex materials with more and more electrons around these tiny green balls that you see here on the screen. We are now ready to come back to where I kind of started. So that is trying to obtain fuels out of air. And the idea is to get compounds of this kind, which you see here on the side of the slide, that our chemical industry knows how to handle. But besides that, we have computers and chemistry. What makes us think that this would actually be possible? Well, there is actually a precedent in human history in which we were able to obtain bread out of air. That takes nitrogen, the Earth's component, and converts it to ammonia. That then is used to synthesize fertilizers in large scales that we use for our crops in agriculture. And this process is so important that if it were not for it, half of the audience of this room would vanish. But don't actually worry, we have this process going on, so we don't need to make any selection right now. So we have nitrogen, combine it with hydrogen, and form ammonia. And this happens because chemists add a little spice to the reaction mixtures. That is like the soul you have, right? So in this case, this is an iron catalyst that makes the reaction happen much faster and much efficiently. So let's complicate a bit more the things, okay? And come back to the picture where we have A and B reacting. We actually can keep track of what happens when there is a catalyst in a reaction. So what it does, it takes our species, makes them jump together, makes them happy somehow, and you actually get to the products. And what a catalyst does is modify our shape of the hills, if you want, that our species have to cross in order to lead us to the right products. And that is why a catalyst accelerates and makes reactions faster. So here I give you an example of a simulation carried out in my research group, where you can see the atoms moving around, dancing on the surface of a catalyst. So it seems quite clear now that we need a catalyst able to foster this transformation and to convert the CO2 that we have in great amounts in our atmosphere into fuels. We now understand, using the techniques I described you, how we can actually obtain methanol, which is also a precursor of a fuel. But in the present ChatGPT era, there is actually another ongoing technological development, and that is the rise of artificial intelligence. That is a very powerful ally to computational chemistry. So what we can do now is, from one side, get a lot of data for several materials using computers. And by taking the use of artificial intelligence together with computational chemistry, we can actually understand better why a given material is able to do some particular thing. So why a given catalyst would be able, or to understand how it would turn or obtain fuels from the air. But it becomes also possible to go the other way around. So given a target, so turning CO2 into fuels, to design and to find and propose the right catalyst able to actually promote this transformation. So let me close with an outlook. We have gone a long time since Schrödinger's time in computational chemistry. We have now a theory for everything, where we can model all matter, and we can keep track of the electrons along the way to predict properties of materials and catalysts. We are working on designing and discovering new catalysts to actually obtain fuels from air. And with all that current technological developments, we may not be that far from having a digital laboratory at our fingertips. Thank you very much.